Hello. So today we are doing this problem called coin change, and the problem says that we that you get coins of different denomination and the total amount of money, and we want to write a function that computes the fewest number of coins that you need to make up the amount. And so if that amount of money cannot be made by any combination of the denominations or the coins that we have, then we need to return -1. So essentially it means we get an amount value and we want to use the minimum number of coins that are passed so that at the end we can get their sum constitutes the amount. So for example, with 11 here and with these 3 coins, we can take basically one other detail is that we can take as much as we want. We can take a coin as many times as we want. So basically we suppose that we have an infinite amount of each coin, and so here we take 5 and then 5 to get 10, and then we take 1 to get 11, and so overall we took 3, and that's the best we can do. If we have just one coin and the amount is 3, this coin value is 2, so there is no way to get 3 using just 2, right? And so we return -1. So that's the idea. So let's see how we can solve this problem. So the first thing to think of is what we want is compute the fewest number of coins that you need to make up that amount. So this description here, the fewest number of coins, kind of tell us exactly what we need to tell us that, because it's the minimum number of coins. So it's a minimization problem. We are optimizing to get the minimum number of coins. So you should directly think about dynamic programming. But before doing that, I'm just going to first do a recursive solution, and then from there we can look at how can the dynamic programming solution work. So one thing is we have an amount and we have a set of coins. We have coin 1, coin 2, coin 3, right? And so we need to be able to take some amount of coins. So let's just try all of them, try all the different combinations. And so in order to try all the different combinations, just start from amount and go through all the coins, right? Go through all the coins, and let's define, for example, coin change helper here, that for a nick helper that for some amount finds the number of coins. So finds the number of coins. And so what we can do is just go through all the coins and check. So use that coin. So basically use that coin, right? And so that would mean using a coin means now we have a smaller amount to find. So for example, let's say we had the amount 11, right? And we took coin 5, right? And then we had 1, 5, 2. And which that's the example, yeah, 1, 2, 5. So if we take coin 5, that means we get 11 minus 5, right? Left. So we have 6 left to find how many coins we need for this one, so that we can get the total amount, right? So that's what I'm doing here. But since I used a coin, the number of coins is 1 plus whatever number of coins is required by this subproblem, right? But since I want to minimize, so let's try this one and see if taking this one and finding the number of coins required by 11 minus 1, let's see if that one is better, or if taking coin 2 is better, or if taking coin 5 is better. And so in order to do that, we will just use minimum of basically whatever we had so far, right? Which is, let's say, call it count, and that's what we will be using, right? And because we are using min, what should we initialize it by? If we initialize it by 0, maybe there is no solution, and that's 0. And so what we need to do for min is give it the maximum value possible, so that any number of coins found will be taken instead. And so to do that, we can just in Python use float infinity, and that's pretty much it. So basically you can consider that this one, the count, we have two choices. We take the coin or don't. and not taking the coin is just using the previous count that we had, right? And so we have the recursive, dividing the problem into a smaller subproblem here, but we didn't think about the base case. So what is our base case here? So our base case is if we kept recursing until the amount became 0, because let's say 10 and then we took 5, and then we called the function again and we took 5, so there is 1 remaining, we called the function again and we took 1, and then we will take 1 minus 1, now it's 0, so what should be the value for 0? So if the amount is equal to 0, then we are done, right? So that means that we can just say, okay, we don't need to use any coin for that, right? So that's 0. But there is also another problem, is because, for example, let's say for 11 we took 5 and then we took another 5, and so now we have just 1 left, and then we came here and tried this coin 5, so that means we are at 1 minus 5, which is a minus 4, right? Which means that's not a solution, so that shouldn't be even considered, right? And so for that one we need to say if the amount left is less than 0, we need to say that we can't, right? And we can't is considered with minus 1, right? And so we can say we can return minus 1. And so that's pretty much it. So we have our base case, so let's just code that solution. And so let's just define this helper with the amount. I'm just going to call it the remaining, because that's what we pass is what's remaining for the amount that we need to make change for, right? So let's just call it remaining like this, and we need to check the base cases, which is these two cases. Let's just replace this with the remaining, and the next case is for let's just replace with this then after that, and so that would be something like this. That's the for loop, and this is the count, and the value I have here is called remaining. There's just one thing, is that what if the value is minus 1? Then we would have 1 minus 1, which would say 0, and that's not really right. And so what I'm going to do is I'm going to just store this in a variable. Let's call a subproblem coins or something, or just subproblem, and then if that's bigger than or equal to 0, that means there was a solution, and so let's consider that. Otherwise it's not a solution, so let's just skip it, right? And then at the end we can just return count. So here you can see we just use the recursive solution with the choices that are possible at each point, right? So the problem is with the indentation. Okay, let's just try again. Yeah, I forgot to call the main function, which is calling this one on the entire amount, right? At the start we have the entire amount to make the change for. Okay, let's submit. Okay, we have a problem because, yeah, so what if for a case like this where there is no solution minus 1, I'm returning infinity, which is just because I didn't find any solution. So what I can do is say this is the result, right? And check if result is, so if it's equal to infinity, that means we didn't find the solution. So let's just return res if res is different than infinity, and if it's infinity we can just return, if it's the max value, that means we couldn't find the solution, and so we can just return minus 1. So let's take this here, let's take this value. Okay, let's submit. Okay, so we get time limited exception here for this case. And that's normal because this problem here does a lot of subcases, does a lot of repetition, because here maybe this amount was already calculated. We already know how many, the minimum number of coins it will take, because we already tried it with a different combination of coins. But in that case, we'll still go ahead and recompute it, which is really a waste. And so solve this kind of issues, we can just use memoization, and this would be now recursion with memoization, so that it guarantees that we don't, that at most we will do the amount time of operation, so that it can be of amount. And so to do that, we can just use a map like this, and here check if the reminder is already, we already calculated for that amount. If we did, then we can just return it right away. And then when we compute here, when we compute the, we save it in the memo table, and then we return it, so that next time if we call with the same amount, we can just return whatever we computed before, because it will be the same, right? If we like found 8 by using one coin, let's say we had coins, let's say 2, and then we had 4, right? And then we had a problem where it's, let's say 8, right? So we can use 2 coins, 2 and 2, and end up with 4, or we can use 4 and end up with 4, right? But with both these sub-problems, it's the same solution, right? So there is no need to do this 2 times. We can just do it once and reuse that, right? So that's what's happening here. And that's pretty much it. So let's run this. Okay, so that passes. So you can see now we don't get the time limited exception that we had earlier. So now since we did the recursion and the recursion with memoization, let's think about doing this using bottom-up dynamic programming, right? So for that, we need a couple of things. We need what is our goal, what is our state function, what is our base case, and what is our recurrence, and what is the order of iteration that we want to use. Order of iteration. So this is just my template that I like to use for dynamic programming problems, and it helps a lot to find the solution. So the goal function is to compute the fewest number of coins, the minimum number of coins, let's call it, the minimum number of coins that you need to make up that amount using the coins that we have, right? And so from that we can probably define a state. And so what matters here in this is the value has to be, the value of the state has to be the minimum, has to be the min number of coins, because in order to obtain the goal function we need to use the value of the state, and so it has to be the minimum number of coins, right? And so, but also one other parameter that we have is the amount, right? And so what we can do is we can have dp of I be the state, and dp of I will constitute the minimum number of coins to make up the amount I, right? That way we can try for I equal to 1, and then maybe use coin 2 and try for I equal to 3, and you can see we can build up using this state. So what is the base case in that case? So dp of 0, so the minimum number of coins to make up the amount 0. Well, that's just 0 coins, right? We don't need to do anything. Now let's try to see what the recurrence we can use. So one hint is what we did here, which is subtract the number of coins, right? And so we know that it's the min of whatever we had before. Let's say we were able to get the amount with a number of coins, a different number of coins. And using this, it would be dp of that amount minus coin, right? So we will need to go through the coins, right? And say dp of I would be, the minimum number of coins would be either the minimum number of the number of coins from the previous using the previous coin, or the number of whichever is smaller, or the number of coins by using this current coin, and then we need to add 1 because we use this current coin basically. And so that's pretty much all we need to do. But for the recurrence, we need to go through i's also, right? And so the order of iteration here would be, we are going to try to get for each amount, right? And so that would be an amount plus 1, because I want to find up until amount, the value amount. And for Python, since the range, if I do just amount, it will stop at amount minus 1, and I want to get the value for amount. And so I would do this, and then I would do the recurrence here. So one thing to think of always when we do this order of iteration, make sure that when we are calculating this state, we are certain that we already computed this substate. And so here, what I want is, if I'm computing the DP of 8, let's say the amount was 10, right? If I'm computing the DP of 8, and I'm using coins, let's say 2 and 4, I want to make sure that I already computed DP of, so this would be DP of, let's say I'm going for coin 2 at this iteration, right? I want to be sure that I'm already computed 8 minus 2, which is 6, right? Because if I didn't, then the value won't work, right? Because it will be probably the initial state, which is infinity. I forgot to initialize this here. So DP would be initialize all to infinity first, because we are looking for the minimum, so we need to initialize with something that will always give us a result. So if we are maximizing, we will initialize with minus infinity, for example. If we are counting, we will initialize with 0, for example. And so here, for when we are calculating DP of 8, we want to be sure that we have DP of 6 already calculated. And that's the case because here our I goes from 0 to the value 8, right? And so we would already have done I equal to 0, and then we will go and we do I equal to 5, we do I equal to 6. So we compute DP of 6, and DP of 6 uses the ones before that, so we already have computed it. And then we will go I equal to 7 until I equal to 8, and at that point we have DP of 6, right? And also when we use the coin 4, the case where we are using the coin equal to 4, if we do DP of 8, 1 plus DP of 8 minus 4, which is 4, we already computed I equal to 4. So it's always a good idea to go through an example to make sure that when you are computing a state and are using a subproblem, a state of a subproblem, that we already computed it using our iteration to make sure that our order of iteration is correct. And that's pretty much it. And so let's code that solution. And so what we need here is we need a DP, and as I said, I'm initializing it to infinity. So this value, the initial value, you need to look at the goal function or the state function, which is, and if it's the minimum, you need to initialize to positive infinity. If it's the maximum, initialize to negative infinity. If it's counting, initialize to 0, and so you get the idea basically. You initialize with something that will make whatever operation you are doing here work, right? And so here we would have float of infinity for in range of amount plus 1. One thing I forgot to mention is the goal function here, which is what we need to return at the end. That would be just DP of amount, because that will tell us exactly the minimum number of coins to make up the amount, right? Which is exactly what we are looking for. And so the base case says that DP of 0 equal to 0, and now we can just do our iteration that we mentioned here. And one thing we need to be careful of is, let's say we had a case we need to be careful of. Let's say the coins here was, we had a coin 9, right? And then we tried with 2, and then tried with coin 4, and then we came at coin 9. So in that case, well, if we try to apply this, we would have 8 minus 9, right? So we would have minus 1, but there is no amount minus 1, that doesn't exist. And we didn't compute it because we started from 0. So this is where it's handy to look at your order of iteration. And so we need to protect against that. And so we need to check here so what should happen? Or the amount should always be bigger or equal to the coin, right? The coin value. And so we need to check that before continuing. The coin value, and then we can return the goal function, which is dp of amount. And so that would be this. Yeah, I don't need this helper anymore. Yep, so I forgot something to handle the case where I couldn't find any solution because, for example, the coins were all bigger, let's say, than the amount, for example. In that case, it will still be initialized to infinity, and I don't want that. And so I'm going to do the same thing as I did for the previous solution, which is if amount. So we are going to return this if it was updated, so it's different than the default value. And then else I'm going to just say I couldn't find a solution, so it's minus 1. Okay, so that should work there. We'll submit. Okay, so that passes. In terms of time complexity for this solution, we are doing one loop here, the amount, and then we are doing then one loop over the coins. So it's O of amount multiplied by number of coins, right? And so if we say like let's say n is the amount or a, and then s is the number of coins, or let's say c is the number of coins, then our time complexity would be just O of a multiplied by c, right? As for the space complexity, we are using only one array here, which is this dp array, and the size of that array is amount, right? Amount plus 1. And so overall the space complexity is just of amount, which is in our case here, let's say just O of a, right? And so that's pretty much it for this dynamic programming solution. There is a different way we can solve it, slightly different, that is just nice to know so that you can get used to the different styles of loops for dynamic programming, which is this order of iteration here doesn't have to be like this. We can do the coins first, and then for each coin, try it on each amount. So start with coin 2 and see how much it will give for amount dp of 2, and then how much it will give for amount dp of 3 and dp of 4, and you get the idea. And with that, we will also have, if you try like yourself to do something like this, like I did here, you will see that the order of iteration works out because the previous states will always be calculated before calculating the state that uses them. And so to do that, we can just flip this one here. And this makes a difference only in cases where, let's say, coins are a smaller number for sure than the amount that we can have. So in that case, it makes sense to have this one as the outer loop. And so we are going to do the same operations. The only thing that changes is the order, and that turns out to be fine. With some problems, it may not, so it always makes sense to try it out on an example beforehand. Okay, so that also passes. Yeah, there is not a big difference, but it's just nice to know that you don't have to always use the same type of loop. And this one has the same time and space complexity also. Yeah, and that's it for this problem. Thanks for watching, and see you next time.